Hello everyone. In this lecture, we want to learn about reciprocal of a linear function. So as you see here, the graph of a linear function is drawn here. It shows this dashed line, and our linear function is y equals x minus 1. And we want to see how the graph of the reciprocal of this linear function, that is 1 over x minus 3, looks like. That's what we want to investigate. The first thing we're going to do about this rational function, which is also known as reciprocal of this linear function, is to find the domain. We know that rational functions are undefined at the roots of their denominators. So here the denominator x minus 3, if you set it equal to 0, x would equal to 3, and that is called non-permissible value of the function. That is, the function is undefined at x equals 3. The reason is very obvious. If you plug in 3 for x, 1 over 0 is undefined. So since division by 0 is not defined, the denominator gives a restriction. And the restriction is that x cannot equal to 3. Therefore, the domain is all real numbers except x equals 3. So x cannot equal to 3 basically. Also, we want to describe the behavior of this reciprocal function or rational function near its vertical asymptote. Now, the vertical asymptote is that vertical line that the graph approaches, but it never touches it. Now, let's see first of all how the graph looks like. So we are going to use the table of values. I've selected here some x values. So x is 2, 2.5, 2.8, 2.9. And we can plug it in the reciprocal function 1 over x minus 3 for x. And then we can evaluate the values of y. And if you do so, you end up with a whole bunch of points. For example, here we have this point with x coordinate of 2, y coordinate is negative 1. And then we have 2.8, negative 5. And then we have like 2.9, negative 10, so on and so forth. And also I have selected some other values for x, and we see that those values are like, for example, 4, 1, or like 3.5 and 2, and then 3.1 and 3.2 and 5, and finally 3.1 and 10. So you see that when the x values, starting from 2, they start increasing bit by bit, and they approach 3, the value of y approaches a huge negative number, like negative 1,000. And when you look at the other table of values, when x approaches 3 from right-hand side, first it's 4 and then 3.5, and then gets closer to 3, 3.2, and it reaches 3.01, we see that the value of y becomes a huge positive number in this case. So that tells us that the graph of the function, which I'm going to show it to you, is in a way that it becomes closer and closer to the vertical line x equals 3 as x approaches 3 from right side and left side. So if x approaches 3 from right hand side, or if x approaches 3 from left hand side, the value of y either becomes extremely large, so the graph approaches positive infinity, or the value of y becomes extremely small, as we saw in the table of values, negative 1,000, and the graph approaches negative infinity. So that shows the behavior of the graph at the neighborhood of its vertical asymptote. And then if we want to describe the end behavior of this graph, what is happening when x approaches positive infinity and negative infinity, there's another table of values that we can investigate. So here x is negative 1 right here. So y is negative 0.25. And then we select the smaller x value, negative 10, right here. And we see what happened. The y coordinate becomes like closer to 0. And if you select negative 100 or negative 10,000, you see the y values are extremely close to 0, but negative. So negative means the points are below the x-axis. So as x approaches negative infinity, negative infinity, the value of y approaches 0 from below the x-axis, basically. And what happens on this other side, in this other table of values, if x is 1, 10, 100, 10,000, if x becomes larger and larger, and eventually approaches positive infinity, we see what happens to the value of y. The value of y gets smaller and smaller. Eventually, it approaches 0, but this time it's a positive 0. So this number here, it's close to 0, but it's positive. This number here is also close to 0, but it's negative. So that tells you that the graph approaches its horizontal asymptote, which in this case is, of course, the x-axis, whose equation is y equals 0, from below if x approaches negative infinity. But if x approaches positive infinity, the graph approaches its horizontal asymptote from above. So that shows the end behavior of the function. In terms of the range of the function, if you want to talk about the range, we should say that the graph of the function shows that f of x, or y, gets close to the line y equals 0, which is the x-axis, but never actually touches that line. Therefore, the only restriction on the range set of the function is that y cannot equal to 0, clearly. So the range of the function is the set of all real numbers except the value of 0. So y cannot equal to 0. And as we said, the domain was again set of all real numbers except that x could not equal to 3, which was the root of the denominator. The equations of vertical and horizontal asymptotes are x equals 3 and y equals 0, respectively. And one more thing here I have to add, and that is whenever you have a reciprocal function, whatever the x-intercept of the linear function is, here you see the x-intercept of the linear function is 3, 0, right? Whatever the x-intercept of the linear function is, that point would represent the vertical asymptote for the reciprocal function. So x equals 3 here for the rational function represents the vertical asymptote. It's a vertical line. But x equals 3 for the linear function, y equals x minus 3, represents the x-intercept. So if instead of a straight line, we have like a parabola, or we have like some sort of other kind of curve, maybe cubic or like quartic, and if we have like 2 or 3 or 4 x-intercepts, and those are the roots of the denominator, then we are going to have 3 or 4 vertical asymptotes accordingly. I hope you understood and learned a little bit more about reciprocal of a linear function. And in the next lectures, we will discuss more on this topic. Thank you.